between the flange and the web. Okay, so now, given all this information, now we're going to calculate the principal stress first. Okay, we're going to calculate the principal stress. And calculating principal stress, I want you to pay attention, okay, when to calculate, where and how and why. Okay, right. So we are going to, I'm going to recap you. Okay, so we're going to draw our free body diagram first. Okay, so from free body diagram, we're going to sketch this overhanging beam. So from here to here, this is our beam. So this is our point A. Then our point B. Then we have our point C. And then finally, we have our point C we don't have, sorry. We don't have anything going up. Then we have point D. So this is your Z. And this is your Y. And point D, you have a force going up. So this is your DY. And this is your BY. So the first thing that we're going to do is construct free body diagram. Okay, why free body? So now we have to map out, or we have to sketch the shear force and bending moment equation. Oh, diagram, not equation. Okay. So this will be taught to you in 2P. So some of you forget in 2P, don't worry, we'll go through it again. Right. So we have a distributed load at the top. Right. So the distributed load is up to point C. So they will be, so somewhere around here, the equivalent load. So this is our equivalent load. So the equivalent load will be equal to 2.4 plus by 0.8 and then times by 50 times 10 to the power 3. Okay, so because this is 50 over here, so 2.4 plus 0.8 times by 50 power 3, so it's equal to 160 times 10 to the power 3 Newton. And then the next thing we have to map out is we have to find out our distances. Okay, so from here to here, we know is equal to 0.8 plus a 2 is equal to 1.6 meters. Right. So from here to here, the overall length is 0.8 plus 0.8 plus by 2.4 minus 1.6 is equal to 2.4. 2.4, not 3.4. 2.4. And then the distance from here to here. So you get your distance right first. Okay, so this is equal to 3.2. Right. So now we're going to carry out a static analysis first to get to our shear force diagram. So we're going to carry out static analysis. So we are going to do summation about moment Z, and we're going to take moment at point D. The whole thing will be equal to 0. So it will be, so sorry, not Z. Okay, this is X, right? Because Z is in the direction, and this is our rotation in the X. Okay, so from here we will have 160 times 10 to the power 3 multiplied by a distance of 2.4 minus by 32, 3.2 by the whole thing will be equal to 0, right? So By, we want to calculate By now, will be equal to 160 power 3 times 2.4 divided by 3.2 is equal to 120,000, okay? Then we do summation about forces that's going up. So you have 120 times 10 to the power 3 minus by 160 times 10 to the power 3 plus by dy. The whole thing is equal to 0. So dy will be 40 times 10 to the power 3. Okay. Then from here, we are going to draw our shear force diagram. But before we draw our shear force diagram, I'll teach you something like the function, how to look at the function. Okay. So we are going to, as I said, this is something extra that you'll learn later, but I want to introduce to you now. Okay. So we are going to form the between, just briefly, okay, between point A to point B, right? Okay, so between point A to point B. So we're going to form, so this is between 0, Z, and up to a distance of 0.8. meters. Okay, so we're going to form the shear force and bending moment equation. Okay, right. So over here, this is your point A, right? So this is your variable X, right? And then over here, you have a load coming down, right? So this is 50 times 10 to the power 3 X. And this equivalent load, because it's evenly distributed, this is X over 2, right? So at the end, the other limit where the variable is, okay, you have your shear force is coming down. And then you have your bending moment that is going in the anti-clockwise direction, okay? And why this direction? Because we assume positive shear, positive bending moment. Okay, so you do your static analysis. Summation about forces in the y direction is equal to 0, right? So you will have minus 50 times 10 to the power 3x minus by v as a function of x. This is equal to 0. So v as a function of x is equal to minus 50 times 10 to the power 3x. Okay, so that is your shear force equation between 0 z to 0.8. Then you take moment in the z-axis. I do apologize. Okay, this is z. I keep on mixing up. So used to the x-axis being x, okay, cube z over 2. My apologies. Okay, let me rewrite this. So minus 50 times 10 to the power 3 z minus by v as a function of z. The whole thing is equal to 0, so I have to change this to z. Okay. So v as a function of z is equal to 50 minus 50 times 10 to the power 3 z. Okay, so m moment, we're going to take moment the x-axis, and at the position Z. So what does this mean over here is we're going to take moment at where I'm drawing my dot now. Okay. Right? Where I'm drawing my dot now. Okay. So from here, probably you guys have seen it in math before. Okay. So from here, you have the 50 times 10 to the power 3 Z multiplied by Z over 2, right? Plus by M Z. They're in the same direction. So M as a function of Z will be equal to minus 25 times 10 to the power 3 Z squared. Okay. So now we're going to look at this function now. Okay, we're going to look at this function now to sketch out our what? Our shear force and bending moment diagram. Okay, so how much space? So I'm going to use the next page. So I'm going to copy this diagram. Okay, so we're going to sketch our shear force and bending moment diagram. Okay, so we are going to have okay, so we are going to see so this is our y-axis, this is our shear force. So we're going to have 80, 60, 40, 20, 0, minus 20, minus 40. And then we're going to have our 0 line. So this is our x. So at this point down here, this is our 0.8. At this point down here, so 0.8 plus 2.4 is equal to 3.2. And over here is our 4. Okay. So if we look at our function that we form, right, our function is minus 50z, right? So we know that we're going to have a negative slope because minus 50. Sorry, this is z again. So minus 50 times by 0.8, right? So minus 50 times by 0.8 is 40. Okay, so minus 40. So this is your first point, right? So it's going to come down here. Okay. So this is at minus 40. Oi. My notepad is not listening today. And then at point B, right, we are going to go up by what? We are going to go up by 120. Okay, so it's go once it reach 100. So from minus 40, it's going to go up by 80 by 120. So it's going to see 80, right? So you'll go up by 120. Then when it reach, okay, so when it reach, so the distributed load will end at here at 0.8. Okay, so we know that the slope is the same. Okay, so this I'm going to copy, I'm going to paste. So the slope will be the same. And once it reach 3.2, it's going to stop. Okay, so over here, so the function will still be the same, only the starting point is different. So it will reach here, you'll be about minus 40. Okay, and why I say you'll stop down there, right, is because of what? So when you have a distributed load, your shear force is going to be a slope, like what what we have seen. Okay, why I would say that you stop at 40 is because at point D, you have 40 Newton going up, right? and then the shear force or the distributed load did not exist between C to D, right? Did not exist between C to D, so it's going to be a straight line. So from here, right, this happened,